There is a number that most scientists prefer not to mention in press conferences about space exploration, a number so devastatingly large that when you truly comprehend it, every fantasy of becoming an intergalactic civilization crumbles like a house of cards. That number is 2,500,000 light-years, the distance to Andromeda, our closest neighboring galaxy. For you to understand what this truly means, let me put it into perspective. If the Milky Way were the size of a €1 coin in your hand, Andromeda would be another coin located almost 3 meters away. Sounds manageable, right? But now, multiply that scale by reality. Each millimeter of that coin represents 1,000 light-years of empty, frozen, lethal space. The Voyager 1 probe, our fastest and most distant human object, has been traveling for 47 years at more than 60,000 kilometers per hour. In all that time, it has barely left our solar system. It has not even truly reached deep interstellar space. If we aimed Voyager directly at Proxima Centauri, the star closest to us, it would take 73,000 years to arrive, 73,000 years to travel 4.2 light-years. Now, take a deep breath and do the math for Andromeda. With Voyager's technology, we would need approximately 1,800 million years to reach the nearest galaxy, 1,800 million years. By the time we arrived, if anything arrived at all, the Sun would have expanded its atmosphere and evaporated the Earth's oceans. Our planet would be a scorched desert, or perhaps it might not even exist. Humanity would be a forgotten fossil, if there were even anything left that could remember. But perhaps you think that Voyager is old technology, that we can go faster, and technically, you are right. The most optimistic proposals for advanced spacecraft using solar sails or nuclear fusion propulsion could reach between 10 and 20% of the speed of light. Impressive numbers compared to what we have now. At 20% of the speed of light, we could reach Andromeda in approximately 12.5 million years. 12.5 million years. From the time the first hominids began to walk upright in Africa until today, barely 7 million years have passed. The entire history of humanity, from the first stone tools to smartphones and spacecraft, has occurred in a microscopic fraction of that time, and we are talking about the one-way trip only. The reality is that the space between galaxies is not like the space between planets, or even between stars. It is an abyss of a scale that our brains evolved to hunt on the African savannas and gather fruit from trees simply cannot process. When astronomers say empty space, they are not referring to a room without furniture. They refer to expanses where you could travel for millions of years without finding absolutely anything. Not a speck of dust, not a stray atom, nothing, except for perfect darkness and the absolute cold at 2.7 degrees above absolute zero. To complicate matters further, that abyss is not still. It is not a calm ocean that we can cross with infinite patience. Intergalactic space is constantly expanding, stretching like an elastic cord that someone is pulling without stopping. Every second that passes, Andromeda and we should be farther apart. Except that the mutual gravity between both galaxies is so strong that we are actually getting closer. But we will talk about that paradox later. Because what matters now is understanding that we live in a universe where the distances are not only enormous, but actively hostile to any attempt to cross them. Think about this. Light, traveling at 300,000 kilometers per second, takes 2.5 million years to cross from Andromeda to your eyes. Light has no mass. It needs no fuel. It does not get tired. It does not age. It is literally the fastest thing that can exist in the universe, according to the laws of physics, and even so, it needs 2.5 million years to make that journey. When you look at Andromeda in the night sky, you are seeing it as it was when our Australopithecus ancestors were just beginning to make the first tools in Africa. Now, imagine trying to send a ship with humans, with all the infrastructure necessary to keep them alive. food, water, air, radiation shielding, redundant life support systems, fuel for course corrections, equipment for repairs, habitable areas, recycling systems. The weight of all of that would exponentially multiply the energy needed to reach significant speeds. We are not talking about small differences. We are talking about each additional kilogram requiring astronomical amounts of additional energy. Scientists at NASA and ESA have calculated theoretical missions to the nearest stars, not to galaxies, just to stars in our immediate neighborhood. And the numbers are discouraging. Project Daedalus, from the 70s, calculated that a robotic mission to Barnard's star, 6 light-years away, would require 54,000 tons of helium-3 fusion fuel. 54,000 tons for a 50-year robotic journey to a relatively close star. Multiply that by the needs of a manned trip to a distant galaxy, and the numbers become literally astronomical in the truest sense of the word. There is another dimension to this problem that is rarely discussed: navigation. At interstellar distances, and much more so at intergalactic distances, navigation errors are magnified exponentially. An error of 1/1000th of a degree in your initial trajectory could make you miss your target by millions of light-years. And there is no GPS in intergalactic space. There are no reference satellites. There are no signals you can use for real-time course corrections. You would be navigating by stars that will have changed position by the time you reach your destination, using mathematics that must predict the positions of objects millions of years in the future. Computer simulations of hypothetical intergalactic journeys reveal another terrifying problem: gravitational drift. Although the space between galaxies is mostly empty, it is not completely empty. There is dark matter, even though we cannot see it. There are weak, but present, gravitational fields. During a journey of millions of years, these tiny gravitational influences would accumulate, deflecting your trajectory in ways that are impossible to predict with precision. It would be like trying to make a perfect billiard shot on a table the size of a continent, with the ball spinning for 1,000,000 years. The chances of success are statistically indistinguishable from zero. And then, there is the time factor. Even if we solved all the technical problems, even if we built a ship that could travel at 20% of the speed of light, even if we could keep generations of humans alive for millions of years, what would we find upon arrival? Andromeda will not be where we see it now. It will have moved. The stars within it will have been born and died. The civilizations that might have existed there will have risen and fallen 1,000 times. We would be chasing a ghost, a mirage of ancient light, trying to reach something that ceased to exist in that form eons ago. The stark reality is that intergalactic distances are not just large, they are so immeasurably vast that they turn any conceivable technology into a useless toy. It does not matter how advanced we become. It does not matter what we discover. It does not matter how long we survive as a species. The abyss between galaxies is, for all practical purposes, infinite. This is our first encounter with the bars of our cosmic cage. The distances between galaxies are not an obstacle that we can overcome with enough ingenuity or determination. They are an absolute wall, built by the fundamental geometry of the universe itself. And this is only the first of many walls we will discover. Because even if we could solve the problem of distance, even if we could make light years not matter, there are even more fundamental barriers waiting for us. Barriers that make distance seem like the least of our problems. The question is no longer how we will get to other galaxies. The question is, why was the universe designed in such a way that it guarantees we never can? Intergalactic distances are terrifying, but at least they are a conceptual problem that we can imagine solving with enough time. Perhaps generational ships, perhaps hibernation, perhaps something we have not yet invented. But there is a much more fundamental barrier, much more absolute, that shatters even the most optimistic fantasies. A barrier that cannot be overcome with ingenuity, patience, or future technology. That barrier is energy. Specifically, the amount of energy needed to move any object with mass at speeds that would make intergalactic travel remotely viable. And when I say amount of energy, I do not mean a lot of energy. I am referring to quantities so obscenely vast that they make all of humanity's energy reserves seem like the spark from a lighter compared to the sunday. Let's start with a concrete number that will help you understand the magnitude of the problem. To accelerate a spacecraft weighing approximately 1,000 tons, roughly the weight of the International Space Station, to 50% of the speed of light, you would need approximately 1,300 million terajoules of energy. To put that in perspective, that is more energy than all the electricity generated by all of humanity in its entire history. All the energy from all the power plants, all the nuclear plants, all the solar panels, all the windmills, all the burning of coal, oil, and gas since we discovered fire. All of that combined would not be enough to accelerate a single ship the size of the ISS to half the speed of light. And that is just to accelerate. You need to brake when you reach your destination, which requires exactly the same amount of energy. So, double that number, and remember, we are talking about reaching only 50% of the speed of light, which means the trip to Andromeda would still take 5 million years. But the problem becomes exponentially worse as you try to go faster. This is due to one of the most beautiful and ruthless equations in physics, the relativistic kinetic energy equation. At low speeds, energy increases quadratically with velocity. You double the speed, you quadruple the energy. But as you approach the speed of light, the relationship becomes exponential, then super-exponential, and finally, asymptotic. That is to say, the closer you get to the speed of light, the more energy you need, and that amount grows to infinity. To reach 90% of the speed of light, you would need approximately double the energy it takes to reach 50%. For 99%, you need 10 times more. For 99.9%, you need more than 20 times the energy of 99%. And for 99.99%, the figures become literally astronomical. We are talking about energies equivalent to the total output of the sun for years. Scientists have calculated that to accelerate a 1,000-ton ship to 99.99% of the speed of light, you would need approximately 4,200 million tons of fuel in a perfect mass-to-energy conversion reaction. 4,200 million tons. For reference, all of humanity consumes approximately 14,000 million tons of oil equivalent per year. You would need almost a third of the annual energy consumption of all human civilization, but not in the form of oil or coal, in the form of perfect fuel, with 100% efficient mass-to-energy conversion. And here is the problem. That perfect fuel does not exist. The most efficient reaction we know of is the annihilation of matter and antimatter. When 1 kilogram of matter meets 1 kilogram of antimatter, they annihilate each other, converting into pure energy according to Einstein's famous equation, E equals mc squared. It is perfect in theory. Each gram of mass converts into approximately 90 petajoules of energy. But antimatter does not grow on trees. You have to manufacture it, and manufacturing it requires exactly the same amount of energy that it will later release upon annihilation. It is like filling a gas tank, using the energy you expected to get from that same gasoline. You end up at net zero. Worse still, our current methods of antimatter production are frighteningly inefficient. For every million units of energy we invest, we get back barely a few units of usable antimatter. The rest is lost as heat, radiation, and secondary processes. CERN, the most powerful particle accelerator in the world, can produce approximately 10 million antiprotons per minute on its best days. Sounds impressive until you do the math. You would need CERN to run continuously for approximately 100 million years to produce a single gram of antimatter, 1 gram. And remember, we need billions of tons. Even if we could magically solve the production problem, storing antimatter is another nightmare entirely. Antimatter cannot touch normal matter, or it annihilates instantly. You need incredibly powerful magnetic fields to keep it suspended in a perfect vacuum. Those magnetic fields require continuous energy, and if something goes wrong, if there is a power failure, if a micrometeorite pierces your containment, all your antimatter annihilates instantly in an explosion that would make thermonuclear bombs look small. But let's assume we solve all those problems. Let's suppose we find a way to produce and store massive quantities of antimatter efficiently. We still face a fundamental problem: the Tsiolkovsky rocket equation. This equation, formulated in the early 20th century, describes a brutal truth about space travel. The majority of your ship's weight is fuel, and that additional fuel requires more fuel to accelerate it, which requires even more fuel to accelerate that fuel, and so on, in a vicious spiral. For an intergalactic journey, the ratio of fuel to payload becomes absurd. Some calculations suggest ratios of 1 million to 1. For every kilogram of payload, instruments, crew, food, water, you would need 1 million kilograms of fuel, and that 1 million kilograms needs to be accelerated too, which requires more energy, which requires more fuel. It is a self-feeding paradox that leads to the point of mathematical collapse. Engineers have proposed creative solutions, the Bussard ramjet, for example, which would collect hydrogen from interstellar space and use it as fuel for continuous nuclear fusion. In theory, you would never run out of fuel, because you would be collecting it as you travel. Problem solved, right? Not exactly. The most recent calculations show that the density of hydrogen in interstellar space is so low that you would need a collector the size of a country to gather useful amounts. And in intergalactic space, where the density is 1,000 times lower, you would need a collector the size of a solar system. The structural forces necessary to hold something like that together at relativistic speeds would instantly tear it apart. Others have suggested solar sails, pushed by giant lasers from Earth. The idea is that the ship carries no fuel. The energy comes from lasers that push it from home. But the numbers, again, are devastating. To accelerate a reasonably sized ship to relativistic speeds using lasers, you would need a laser installation that consumed the total energy output of the sun, literally. And you would need to keep that laser perfectly focused on a ship moving away at relativistic speeds for decades or centuries. An aiming error of 1,000th of a second, and you lose the ship forever. There is also the proposal of nuclear bombs. Project Orion, from the 60s, suggested launching nuclear bombs behind a ship and surfing the blast wave. It would work, in theory. In fact, it is one of the few propulsion proposals that we could actually build with current technology. The problem is that you would need millions of nuclear bombs, millions, for a trip to the nearest star. For an intergalactic journey, you would need more nuclear bombs than there are atoms on Earth. Obviously, impossible. Every proposed solution eventually hits the same wall. The energy required for intergalactic travel exceeds the energy available in the system we want to use. It is like trying to empty the ocean using the ocean's own water. No matter how efficient your pump is, it will never work, because the task requires more resources than the system can provide. And this brings us to the most devastating revelation of all. Even if we could build a perfect antimatter engine, even if we could solve all the engineering problems, even if we could harvest unlimited amounts of energy from the sun or from nuclear fusion, we would still hit an absolute barrier. The speed of light is not just a speed limit, it is an energy limit. As you approach the speed of light, the energy required to accelerate even 1 more gram approaches infinity. Literally, infinity. It does not matter how much energy you have. It is never enough to reach the speed of light, because the universe has placed a wall of infinite energy right at that limit. Physics is not being cruel. Physics is being absolute. The laws that allow energy to exist, that allow atoms to exist, that allow you to exist. Reading these words are the exact same laws that guarantee you can never accelerate fast enough to make intergalactic travel viable. It is not a matter of technology. It is not a matter of time or patience or ingenuity. It is a matter of fundamental laws of the universe that cannot be broken, bent, or avoided. The energy barrier is not an obstacle that we can eventually overcome. It is an absolute wall, inscribed in the very structure of reality. And this wall has an even more devastating consequence that we have not discussed yet. A consequence that makes the problems of distance and energy seem trivial in comparison. Because even if we solved both, even if we found a magical way to travel fast without impossible energy, there is a third barrier waiting for us. A barrier that guarantees that any intergalactic traveler would be doomed to a fate worse than death. The absolute and eternal isolation from the rest of humanity. Imagine that we finally achieve it. Imagine that we solve the problems of distance and energy with some miraculous future technology. We build a ship that can travel at 90% of the speed of light, and we send it toward Andromeda with a crew of brave explorers. It is the greatest moment in human history. The cameras transmit as the ship moves away from Earth, as it crosses the Moon's orbit, as it passes Mars, Jupiter, leaves the solar system, and enters the interstellar abyss. And then, something happens that nobody fully anticipated in the simulations. Something that physicists knew would happen, but whose existential implications had never truly been discussed in public. The messages from the ship begin to arrive more and more spaced out. Not because the crew is sending fewer messages, but because each signal takes longer to arrive. After 1 year, there is a 1-year delay. After 10 years, a 10-year delay. After 100 years, your great-great-grandchildren are receiving messages from people who died decades ago. But this is only the beginning of the problem. The real horror begins when you consider what happens to radio signals at relativistic speeds. When something moves very fast away from you, the electromagnetic waves it emits are stretched. This is the famous Doppler effect, the same one that makes an ambulance siren sound lower pitched as it moves away. But at speeds close to light, this effect does not just change the pitch, it completely destroys the signal. A radio signal sent from a ship traveling at 90% of the speed of light undergoes an extreme redshift. The frequencies are stretched so much that a signal sent in the FM radio band would arrive on Earth as extremely low-frequency radio waves, almost undetectable, and this gets exponentially worse with speed. At 99% of the speed of light, the signals are stretched so much that they become practically impossible to detect, even with the most sensitive radio telescopes. But the Doppler effect is barely the first layer of this communication hell. There is something much worse waiting: time dilation. Einstein proved that time is not absolute. Time flows at different rates, depending on how fast you are moving. At normal speeds, this difference is microscopic, irrelevant. But at relativistic speeds, the difference becomes dramatic, devastating, existential. For a ship traveling at 90% of the speed of light, for every 1 year that passes for the crew, approximately 2.3 years pass on Earth. Sounds manageable, right? A mismatch you could compensate for in your calculations. But at 99% of the speed of light, the ratio is 1 to 7. For every 1 year, for the crew, 7 years on Earth. At 99.9%, it is 1 to 22. At 99.99%, it is 1 to 70. Now, think about what this means for communication. Imagine you are part of the crew, and you send a message to Earth saying, "Everything is fine. We have completed the first year of our journey." That message travels at the speed of light back to Earth. But while that message travels, Earth continues to age much faster than you. By the time your first year completed message arrives on Earth, decades have passed. Your children are elderly. Your grandchildren have grandchildren. The world you left no longer exists, and when Earth replies to your message, its response takes decades to reach you. But to you, feeling it in subjective time, it seems as if Earth simply stopped responding. Messages arrive more and more spaced out, more and more out of sync with your reality. The replies you receive are to questions you asked months ago, according to your clock, but which were sent decades ago, according to Earth's clock. A study published in 2024 by physicists at the University of Oxford modeled this exact scenario and reached a devastating conclusion. At the speeds necessary to make intergalactic travel viable, coherent two-way communication becomes physically impossible. Not difficult, not complicated, impossible. The temporal desynchronization is so severe that any attempt at conversation collapses into a chaos of messages arriving in the wrong order, with lost context, with references to events that have not yet happened, or that happened so long ago they are no longer relevant. Imagine trying to have a conversation where every word you say takes a year to reach the other person, and their reply takes another year to get back to you. But on top of that, time is flowing at different speeds for both of you. It would be like trying to play chess by postal mail if the letters arrived randomly out of order and the other person aged 10 years for every move you make. But there is an even deeper layer of horror to this problem. It is not just that communication is difficult or delayed. It is that it eventually becomes literally impossible to maintain a coherent signal. Electromagnetic signals lose energy as they travel. They disperse, they weaken, they get contaminated by cosmic noise. At interstellar distances, you need massive antennas and enormous transmission power just to send simple messages. At intergalactic distances, the amount of energy needed to send a detectable signal becomes prohibitive. Scientists calculate that, to send a simple radio message from Andromeda to Earth that could be detected with our most powerful radio telescopes, you would need an antenna the size of a planet, transmitting with a power equivalent to the total output of several stars. And that is just to send something equivalent to a few words. To send video, audio, complex scientific data, you would need energies so vast that you would basically need a Type 2 civilization on the Kardashev scale, one that can harness all the energy of its star. And this assumes that both ends of the communication are stationary. But remember, the ship is traveling at relativistic speeds. The Doppler effect is distorting all the frequencies. Time dilation is desynchronizing all the clocks, and the distance is constantly increasing. Every second that passes, the ship is millions of kilometers farther away. Every day, tens of billions of kilometers. Every year, distances that defy comprehension. There is also another phenomenon that is rarely mentioned: the relativistic aberration of light. At near-light speeds, your perception of the universe changes radically. The stars in front of you seem to concentrate into a single bright point, while the stars behind you disappear. The entire sky is distorted, and the signals you receive from Earth do not arrive from where you expect. They arrive angularly displaced due to your extreme velocity. You need to constantly calculate where to aim your antennas, not toward where you see Earth, but toward where Earth will be when your signal arrives, compensating for both your movement and time dilation. The complexity of maintaining communications under these conditions is not just technical, it is existential. You are trying to maintain contact with a world that is aging at a different rate, that is separated by distances that cause signals to take years, decades, or centuries to travel, where every message you send is a time capsule from a version of you that technically no longer exists by the time the message arrives. Psychologists who have studied extreme isolation in Antarctica, in nuclear submarines, in space simulation missions, all agree on one thing: humans need regular social connection to maintain sanity. Not occasional, regular, daily, ideally. When that connection is delayed too long, when replies take weeks instead of seconds, human psychology begins to break. People develop depression, anxiety, psychosis. Now imagine that replies do not take weeks, they take years, decades. That every message you send is essentially a letter thrown into the void, with no real hope of a meaningful response. That every day that passes takes you further away from the only species you can genuinely communicate with. That you are doomed to spend the rest of your life, and the lives of your children, and the lives of your children's children, in an isolation so complete that no human in history has ever experienced it. This is not exploration, it is exile. It is a voluntary banishment to a solitude so profound that it becomes a form of living death. You would still be alive, you would still be thinking, feeling, existing, but you would be completely, irrevocably separated from everything that makes human life meaningful. No real-time conversations, no love shared in the moment, no ability to comfort someone who is suffering or celebrate with someone who triumphs. And here is the cruelest paradox of all. The very speed that makes the journey possible is what makes the connection impossible. To travel fast enough for the intergalactic journey to be viable within a human lifetime, you need to go so fast that communication breaks down completely. You cannot have both. It is physically impossible. You can reach another galaxy, or you can maintain contact with home, but you cannot do both. The universe forces you to choose, and both options are variations of tragedy. Intergalactic travelers would not be explorers. They would be ghosts, entities trapped between worlds, unable to return to the one they left, nor truly belong to the one they are trying to reach, wandering the abyss for generations, sending messages that no one will answer in time, receiving echoes from a world that died long ago, condemned to a form of existence that no conscious being should ever experience. And this cosmic loneliness is not the only problem travelers face, because while they float in that absolute silence, as Earth ages at different rates and communications fade into cosmic noise, the universe itself is actively working against them in a way that makes all previous problems seem trivial. An invisible, unstoppable force, guaranteeing that every second they spend traveling, their destination moves further away, faster than they are approaching. There is a force in the universe that few truly understand. A force so strange and counterintuitive that when it was first discovered, even the world's best physicists refused to believe it. A force that neither pushes nor pulls, that has no identifiable source, that cannot be blocked or avoided. A force that is, at this very moment, pushing every galaxy away from every other galaxy at speeds that are constantly increasing. That force is the expansion of space itself. In 1929, the astronomer Edwin Hubble made a discovery that forever changed our understanding of the cosmos. He observed that practically all distant galaxies were moving away from us. And the strangest part of all is that the farther away a galaxy was, the faster it was moving away. It was not that the galaxies were moving through space, it was that space itself, between us and them, was expanding, stretching like a cosmic elastic band that someone is pulling non-stop. The relationship he discovered is now known as the Hubble-Lemaitre law, in honor of Hubble and the Belgian priest Georges Lemaitre, who first proposed the idea mathematically. The law is deceptively simple. For every 3.26 million light-years of distance, galaxies move away approximately 70 kilometers per second faster, 70 kilometers per second per megaparsec, in astronomical terminology. It sounds like a small number until you start to do the calculations. Andromeda, at 2.5 million light-years, should be moving away from us at approximately 54 kilometers per second due to the expansion. In fact, it is moving closer at approximately 110 kilometers per second, because the mutual gravity between the two galaxies is strong enough to overcome the expansion. We are the exception. Andromeda and the Milky Way are destined to collide in approximately 4,000 million years. But beyond our local group of galaxies, beyond the few dozen galaxies that are gravitationally bound to us, the expansion completely dominates. A galaxy, at 300 million light-years, moves away at approximately 6,500 kilometers per second. A galaxy at 3,000 million light-years moves away at 65,000 kilometers per second, and this is where everything completely falls apart. At approximately 14,000 million light-years away, galaxies are moving away from us at the speed of light. Read that again, because it is important. At 14,000 million light-years away, roughly the size of the observable universe, Galaxies are moving away at 300,000 kilometers per second, and beyond that point, they move away faster than the speed of light. This does not violate special relativity, because the galaxies are not moving through space faster than light. It is the space between us and them that is expanding faster than light can cross it. This is the ultimate cosmic trap. Imagine you are on a giant cosmic treadmill that is constantly accelerating. No matter how fast you run, the treadmill moves faster. Eventually, it reaches a point where, even running at the maximum possible speed, the speed of light, you are still moving backward instead of forward. That is exactly what potential intergalactic travelers face. Now, Andromeda is special because it is close enough for gravity to overcome the expansion. But let's say we aim for another galaxy, one that is farther away. The Triangulum galaxy, for example, at approximately 3 million light-years, or the M87 galaxy, at approximately 55 million light-years. For these galaxies, the expansion is actively working against us. The calculations are brutally simple and devastating. If we built a ship that could travel at 99.99% of the speed of light, and aimed it at a distant galaxy during the journey, the space between us and that galaxy would continue to expand. Every year we travel, the target distance increases, not only because of the space we have not yet crossed, but because of the new space being created while we travel. It is like trying to swim to the shore while the current pulls you out to sea. Except, this current does not just pull you back, it accelerates constantly. With every stroke you take, the current gets a little stronger, and there is no way to swim faster, because you are already swimming at the maximum speed physics allows. A study from the California Institute of Technology in 2022 modeled this exact scenario. They calculated that for a galaxy located more than 4,600 million light-years away, known as the Hubble horizon, it is physically impossible to reach it, no matter what technology you use. This means that approximately 94% of the galaxies in the observable universe are already beyond our reach. Not because they are too far away in the traditional sense, but because space is expanding so fast that we can never send even light to reach them. They are observable in the sense that we can see the light they emitted billions of years ago, but they are unreachable in the sense that we will never be able to visit them. And it gets worse. The expansion of the universe is not constant, it is accelerating. In 1998, two independent teams of astronomers discovered that the universe is not only expanding, but it is expanding faster every year that passes. They won the Nobel Prize in Physics in 2011 for this discovery. This acceleration is attributed to something called dark energy, a mysterious form of energy that permeates all of space and pushes the universe to expand faster and faster. The practical consequence of this is terrifying. The reachable horizon is shrinking. Galaxies that we could theoretically reach today, if we had the technology, will be beyond our reach in 1 million years. Galaxies that will be beyond our reach in 1 billion years will be beyond our observable horizon in 10,000 million years. The accessible universe is shrinking as we speak, slowly disappearing behind a cosmic event horizon that we can never cross. Think about the existential implications of this. Civilizations may exist in distant galaxies at this very moment. Civilizations that perhaps are looking at our night sky, wondering if there is anyone else out there. And we are here, wondering the same thing about them. But due to cosmic expansion, we will never meet. We will never exchange signals. We will never share knowledge. We are permanently isolated, not by choice or lack of technology, but by the fundamental structure of space-time. And this applies even to galaxies within our current theoretical reach. Andromeda, which we could reach because gravity overcomes the expansion, is the rare exception. For practically every other galaxy, even those within hundreds of millions of light-years, the expansion means the journey would take much longer than the current distance suggests, because you would be chasing a target that is constantly moving away. Imagine aiming for a galaxy 500 million light-years away, with a ship traveling at 99.99 percent of the speed of light, calculating only the travel time without considering the expansion, you would need approximately 500 million years. But during those 500 million years, space has expanded. The target galaxy is now approximately 600 million light-years away. You need to travel another 100 million years, but during those 100 million years, it expands more. It is a race you can never win, because the finish line is moving away faster than you can run. Mathematicians call this an asymptotic limit. You get closer to your target, but you never fully reach it. It is like trying to reach the horizon. You walk toward it, and it always seems to be the same distance away, always unreachable, always beyond your next step. And then, there is the even darker reality of accelerated expansion. Cosmologists predict that in approximately 100 billion years, due to the continuous acceleration of the expansion, all galaxies outside our local group will have disappeared beyond the cosmological horizon. Their light will never reach us. They will vanish from the night sky, as if they had never existed. Future civilizations in our galaxy will look at the sky and see only darkness. They will have no way of knowing that a larger universe, filled with billions of other galaxies, ever existed. This is perhaps the loneliest possible form of universe. One where intelligent life inevitably arises, looks at the cosmos, and remains permanently isolated from any other intelligent life by forces it cannot control, overcome, or even resist. The universe is designed, by the sheer chance of its fundamental laws, to keep civilizations isolated on ever-shrinking cosmic islands. But here is the final paradox. Even if we could somehow overcome the expansion, even if we found a way to travel faster than space expands, we still crash against the barriers we already discussed. The energy remains impossible, the distances remain insurmountable, communication remains unfeasible. The expansion of the universe is not the only problem. It is simply another nail in the coffin of intergalactic dreams, another fundamental law that says no in the most absolute way possible. And this law has a silent accomplice, another aspect of physics that guarantees our imprisonment, an accomplice that has nothing to do with distances, or energy, or cosmic expansion, an accomplice that is within the very equations that describe how time, space, and velocity work. Einstein's equations, which when you fully understand them, reveal that even in a universe without expansion, even with infinite energy, we would still be prisoners of our own galaxy for reasons that are perhaps the most fundamental of all. In 1905, a 26-year-old employee of the Swiss Patent Office published a paper that would forever change our understanding of the universe. Albert Einstein, a name we all now know, proposed something so radical, so counterintuitive, that even today, more than 100 years later, our minds struggle to fully accept it. He proposed that time is not absolute, that space is not fixed, that both are malleable, flexible, dependent on the observer, and most importantly for our discussion, that nothing with mass can reach the speed of light. This last statement is not a suggestion. It is not a technological limitation that we can overcome with enough ingenuity. It is a fundamental law of the universe, as inviolable as the conservation of energy, or the fact that 2 + 2 = 4. And this law has devastating consequences for any civilization that dreams of intergalactic travel. The central problem lies in an equation called the Lorentz factor, represented by the Greek letter gamma. This equation describes how time, mass, and length change as you approach the speed of light. At normal speeds, the Lorentz factor is practically 1, which means there are no noticeable effects. Your car, traveling at 100 kilometers per hour, experiences relativistic effects so microscopic that they are completely irrelevant. But as you approach the speed of light, the Lorentz factor begins to grow. At 50% of the speed of light, it is approximately 1.15. This means your clock runs approximately 15% slower than the clock of someone at rest. It does not sound so dramatic, right? But watch what happens as you accelerate more. At 80% of the speed of light, the factor is 1.67. At 90%, it is 2.30. At 95%, it is 3.2. At 99%, it is 7.1. You can already see the trend. The numbers start to grow faster and faster. At 99.9% of the speed of light, the Lorentz factor is 22.4. At 99.99%, it is 70.7. And here is the deadly problem. For intergalactic travel to be viable within a human lifetime, you need enormous Lorentz factors. Andromeda is 2.5 million light-years away. If you travel at 50% of the speed of light, it takes you 5 million years according to Earth's time. Useless. Even at 99% of the speed of light, it is approximately 2.5 million years of Earth time. Although for you, it would be approximately 350,000 years, thanks to time dilation. Still completely unviable. To reduce the travel time to something remotely practical, say 100 years of subjective time for the crew, you would need a Lorentz factor of approximately 25,000. This corresponds to a speed of 99.9999992% of the speed of light. And this is where relativistic physics twists the knife. The energy required to reach that speed is absolutely prohibitive. Remember, the relativistic kinetic energy equation. At low speeds, energy is simply 1/2 of the mass, multiplied by the velocity squared. Simple, linear, manageable. But at relativistic speeds, the equation transforms. Relativistic kinetic energy is the mass, multiplied by c squared, multiplied by the Lorentz factor, -1. And when the Lorentz factor is 25,000, you are multiplying your ship's mass by 25,000 times the speed of light squared. The numbers become obscene. For a 1,000-ton ship, the energy needed to reach a Lorentz factor of 25,000 is approximately 2.2 times 10 to the power of 24 joules. To put that in perspective, that is approximately the energy the sun emits in 2 full weeks. You would need to capture all the sun's energy for 2 weeks and focus it perfectly on accelerating your ship. And that is just to accelerate. You need the same amount to brake, and this assumes perfect efficiency, something physically impossible. In reality, with the efficiencies we can achieve, you would probably need 100 times more energy. We are talking about the total output of the sun for almost 3 years for a single ship on a single journey. But even if we could magically solve the energy problem, relativity has other unpleasant surprises waiting for us. One of the most disturbing is the twin paradox, amplified on an intergalactic scale. You know the basic version. One twin travels into space at relativistic speeds, while the other stays on Earth. When the traveling twin returns, they have aged less than the twin who stayed home. It is a real effect, experimentally verified 1,000 times. Now, amplify this to an intergalactic journey. Imagine you set off for Andromeda with a Lorentz factor of 25,000. For you, the journey takes 100 years. You live a whole life, exploring during the trip. Perhaps you have children, even grandchildren. Finally, you decide to return home. Another century of subjective time, 200 years total for you. But when you return to Earth, approximately 5 million years have passed. 5 million. The civilization you knew no longer exists. The language you speak is unintelligible. Your friends, family, your entire species as you knew it, everything has been gone for eons. The continents have moved, species have evolved. The Earth you left is literally an alien world. Now, there is no going home. Technically, you return to the same planet, but that planet has changed so much that you might as well be on another world. You are a timeless ghost, a living anachronism, someone completely disconnected from their own time. This is not speculative science fiction. It is a direct mathematical consequence of Einstein's equations. Inevitable, inescapable, absolute. There is also the problem of relativistic mass. As you accelerate, your effective mass increases by the Lorentz factor. This does not mean you gain additional atoms, but that your inertia increases. It becomes harder and harder to accelerate further. At 99.99% of the speed of light, your effective mass is 70 times greater than your rest mass. This means that any force you try to apply to accelerate more has to overcome 70 times more inertia, and this creates a vicious feedback loop. You need more energy to accelerate more, but as you accelerate, your effective mass increases, which requires even more energy to accelerate, which increases your effective mass even more. It is an exponential curve that shoots toward infinity. As you approach the speed of light, your effective mass approaches infinity, and the energy needed to give you even a small additional acceleration also approaches infinity. This is not a rhetorical exaggeration, it is mathematically literal. At the limit where your velocity approaches c, the speed of light, your effective mass diverges to infinity. It would require infinite energy to accelerate an object with mass to exactly the speed of light. Infinite, not a very large number, literally infinite. The universe has placed a wall of infinite energy right at that limit, guaranteeing you can never cross it, and there is more. At extremely relativistic speeds, the universe in front of you begins to behave in strange ways. The photons from the cosmic microwave background, normally harmless, with temperatures of barely 2.7 Kelvin, undergo a blue shift so extreme that they become deadly gamma radiation. At a Lorentz factor of 25,000, these photons would hit your ship with energies equivalent to high-energy gamma rays, constantly bombarding you with lethal radiation. Engineers have calculated that you would need shields several meters thick, made of dense materials, just to protect yourself from this radiation. But those shields have mass, and that additional mass requires more energy to accelerate, and more mass for fuel, and more shields to protect that fuel. It is another vicious spiral with no elegant solution. Even interstellar dust, normally invisible and irrelevant, becomes a mortal danger at extreme relativistic speeds. A dust particle, the size of a grain of sand, hitting your ship at 99.99% of the speed of light, would release energy equivalent to several atomic bombs. Every speck of dust is potentially a catastrophic explosion. You would need to constantly detect and avoid them, or have shields so massive and resistant that the additional weight would make the journey impossible. Then there is the problem of relativistic navigation. At near light speeds, the stars in front of you seem to concentrate into a bright circle due to the aberration of light. The stars behind you disappear. Your perception of the entire cosmos is distorted. Calculating a trajectory becomes incredibly complex, because you have to compensate not only for the movement of your target during the journey, but also for the relativistic effects on your perception of space-time itself. And all of this assumes you can accelerate and brake gently. But humans can only tolerate a certain amount of acceleration before dying, approximately 3 to 4 times Earth's gravity, sustained for long periods. To accelerate to 99.99% of the speed of light, with an acceleration of 3 gravities, would take approximately 1 year. Seems manageable, but that year of acceleration requires massive amounts of fuel, burning constantly, and then you need another year of deceleration upon arrival, and the same for the return. 4 total years of acceleration and deceleration for a single round trip. During all that time, you are burning fuel at phenomenal rates. Calculations show that for a complete trip to Andromeda and back, even with perfect matter-antimatter propulsion, you would need to carry approximately 99.99% of your ship's mass as fuel. Only 0.01% can be payload, crew, instruments, everything else. That means that to have a 1,000-ton habitable module, you would need a ship with an initial mass of almost 10 million tons. 10 million tons. For reference, the largest ship ever built, the supertanker Seawise Giant, weighed approximately 650,000 tons. You would need to build something 15 times more massive than the largest ship in human history. Except this would have to operate in the vacuum of space, withstand extreme radiation, and burn antimatter in a perfectly controlled manner for years. Relativity is not cruel. Relativity is absolutely indifferent. The same equations that beautifully describe how the universe works, that predict with perfect accuracy the behavior of everything from subatomic particles to black holes, are the same equations that forever close the doors to intergalactic travel. Not because Einstein said no, but because the mathematical structure of space-time itself says no. And these relativistic barriers assume we can build the ships, generate the energy, and solve all the engineering problems. But there is a final obstacle that we have not discussed yet. An obstacle that has nothing to do with physics, or mathematics, or engineering. An obstacle that is within ourselves. Our fragile bodies evolved to thrive on the surface of a specific planet, surrounded by a protective magnetic field, bathed in the radiation of a specific star. Bodies that, when you take them out of that perfect environment and launch them into the intergalactic abyss, simply fall apart. We have talked about impossible distances, prohibitive energies, broken communications, and a universe that expands to push our destinations away from us. We have discussed the barriers of relativity that make time itself become the enemy. But there is a final barrier that is perhaps the most intimate, the most personal, the most devastating of all. A barrier that is not in the stars, nor in the equations, nor in the fuel limits. It is in our own bodies. Humans evolved over millions of years in a very specific environment. The surface of the Earth, bathed in the radiation of a G-type star, protected by a planetary magnetic field that deflects lethal charged particles, surrounded by an atmosphere that filters the most harmful ultraviolet rays, with a precise gravity of 9.8 meters per second squared. Every cell in your body, every biological system, every metabolic process is optimized for these exact conditions. And when you leave that protective environment, when you venture into deep space, and especially into the intergalactic abyss, your body begins to fail in ways that are both inevitable and terrifying. Let's start with radiation. On Earth, you are protected by two invisible but absolutely crucial shields. The Earth's magnetic field deflects most of the solar wind, those charged particles that the sun constantly throws into space. The atmosphere absorbs cosmic radiation, those high-energy protons and atomic nuclei that constantly rain down from deep space. Together, these shields reduce your radiation exposure to levels your body can handle, that your DNA can repair. In interplanetary space, say, on a trip to Mars, you lose the atmospheric protection, but you still have some protection from the sun's magnetic field. Radiation exposure increases dramatically. Astronauts on the International Space Station receive approximately 50 to 200 times more radiation than on the Earth's surface, enough to significantly increase their risk of cancer, but manageable for missions of a few months. In interstellar space, you lose even the protection of the sun's magnetic field. Cosmic radiation hits you unfiltered, but at least you are still inside the Milky Way, where the galactic magnetic field provides some minimal protection. NASA studies estimate that an interstellar journey of decades would expose astronauts to radiation doses almost guaranteed to cause cancer. But in intergalactic space, all of this disappears. There is no galactic magnetic field protecting you. There is no solar heliosphere. There is nothing except the absolute vacuum and unfiltered radiation coming from all directions. Cosmic rays with energies so high, they can pass through meters of shielding. Particles that can fragment atomic nuclei in your cells, creating secondary cascades of even more harmful radiation. The calculations are brutal. Even with several meters of water or polyethylene shielding, materials that are relatively good at blocking radiation, an intergalactic traveler would receive cumulative doses that would destroy their bone marrow, collapse their immune system, and guarantee multiple aggressive cancers. And that additional shielding has mass that needs to be accelerated, mass that makes the energy problem even more impossible. Some have proposed using artificial magnetic fields to deflect charged particles, essentially recreating Earth's magnetic field around the ship. But the necessary fields would have to be enormous, on the order of kilometers in diameter, and would require massive amounts of energy to maintain continuously for millions of years. And they would only protect against charged particles. Gamma rays, neutrons, other forms of uncharged radiation would pass right through any magnetic field as if it were not there. Then there is the problem of time. Even if we could perfectly shield you from radiation, even if we could create an impenetrable shield, intergalactic travel takes an incomprehensibly long time. We have discussed the millions of years needed, even at relativistic speeds, and humans do not live for millions of years. We live for decades, 80 years if we are lucky. The obvious solution is hibernation or suspended animation. Freeze the crew, put them in some kind of metabolic stasis, wake them up on arrival. Science fiction makes it look simple. The reality is devastatingly more complicated. We have managed to preserve cells, small tissues, even some organs through cryopreservation. But a complete human, an integrated system of interdependent organs, with a brain containing 86 billion neurons, each with thousands of synaptic connections, is incomparably more complex. When you freeze living tissue, the water inside the cells forms ice crystals that pierce the cell membranes like microscopic blades. The cells burst, the tissues disintegrate. Scientists have developed chemical cryoprotectants that prevent the formation of ice crystals. They work reasonably well for small samples. But for a complete human body, you would need to perfuse these chemicals through every tissue, replace all the water in every cell. And these chemicals are toxic in high concentrations. The dose needed to completely protect you would probably kill you before you could be frozen. Even if we solved the freezing problem, the thawing problem is equally difficult. You need to heat the body perfectly, uniformly. If some parts heat up faster than others, the temperature gradients cause massive structural stress. Tissues crack, organs fail, and the brain, the most delicate structure of all, would be particularly vulnerable. Your memories, your personality, everything that makes you you, is stored in incredibly fragile patterns of synaptic connections. A single error in the thawing process could destroy them irreversibly. And this assumes the hibernation process is done only once. You freeze, you travel, you thaw. But on a journey of millions of years, problems will inevitably arise that require intervention. System failures, meteorite damage, the need for course corrections. Someone needs to be awake to handle emergencies, which means multiple cycles of freezing and thawing. Each cycle accumulates more damage. After dozens or hundreds of cycles over millennia, the cumulative damage would likely be lethal. Alternatively, you could have generation ships so large that an entire population lives, reproduces, and dies during the journey. The great-grandchildren of the great-grandchildren of the great-grandchildren of the original crew eventually reach the destination. But this introduces a completely different set of biological problems. To maintain a genetically viable population for millions of years, you would probably need at least several thousand individuals. Any smaller population would suffer from inbreeding depression, accumulation of deleterious mutations, and eventual genetic collapse. And those thousands of people need food, water, air, habitable space. You need complete, closed ecosystems that can perfectly recycle all resources for eons without failure. A single collapse in water recycling or food production, and the entire population dies. Experiments in closed biospheric systems here on Earth have been consistently discouraging. Biosphere 2, the most ambitious experiment of its kind, collapsed after only 2 years. Oxygen dropped to dangerous levels, carbon dioxide rose. Species began to go extinct, and that was with only 8 people in a relatively large, well-designed environment, with Earth right outside, if something went wrong. Now imagine maintaining a closed ecosystem, not for 2 years, but for 2 million years. for 100,000 human generations. The odds of nothing failing catastrophically during that time are statistically indistinguishable from zero. A plague that kills a critical crop, a mutation in the recycling bacteria that makes them inefficient, a cascading failure where one collapsing system triggers the collapse of others. Any of these errors would be the end of the entire mission. But even assuming perfect ecosystems, there is the psychological problem. Humans did not evolve to live in confined spaces for generations. We evolved as nomads in open spaces, with distant horizons and changing skies. Prolonged confinement causes depression, anxiety, psychosis. Studies in nuclear submarines, Arctic stations, high-security prisons all show the same pattern. Prolonged confinement degrades mental health, even in the most stable individuals. And we are not talking about confinement for years or decades, but for the entire lives of thousands of generations. Children born on a ship live their entire lives without ever seeing a real horizon, without feeling rain, without walking on solid ground, and then die, knowing their children will experience the exact same thing. The probability of social collapse, rebellion, and violence is extremely high. Some psychological studies suggest that after several generations, the population would lose even the motivation to continue the mission. Why should the great-great-grandchildren of the original crew care about reaching a destination they will never see, following the dream of ancestors who died centuries ago? It is likely they would eventually reject the mission, change course, or simply let the systems collapse, because the idea of a destination has become abstract and meaningless. There is also the problem of evolution. Over millions of years in an artificial environment, humans would inevitably evolve. Natural selection would favor traits adapted to the ship's environment, not the destination's environment. By the time they arrived, if they arrived at all, they might be a completely different species. Their bodies adapted to artificial gravity, their eyes adapted to artificial light, their immune systems never exposed to natural pathogens. They would be unable to survive on a real planet, even if they found one. And then there is the most fundamental problem of all: purpose. Intergalactic journeys would take so long that the civilization that initiates them would look nothing like the civilization that benefits from them. Ships launched today would arrive in an era where humanity, as we know it, likely does not exist, replaced by post-humans, artificial intelligences, or perhaps nothing at all, if we go extinct in the meantime. Does it make sense to invest astronomical resources in a mission that will benefit entities so far removed from us in time and evolution that they would effectively be aliens? Does it make sense to condemn generations of humans to live and die in transit, to reach a goal that they might not even remember why it was important? Human biology is not a technical obstacle we can engineer around. It is a fundamental limitation that reflects the fact that we are products of a specific planet, evolved over eons to thrive in very particular conditions. Taking us out of those conditions for cosmological periods is not exploration. It is a slow form of extinction. Every system in your body is screaming that we were not designed for this, that our place is here, on this planet, under this star, protected by these magnetic fields, that the dreams of becoming intergalactic nomads are fundamentally incompatible with the reality of what we are as biological organisms. And all these biological barriers operate together with the physical barriers we already discussed. They are not separate problems you can solve one by one. They are intertwined aspects of a single, devastating truth. The universe, in its fundamental structure, guarantees that biological species remain confined to their home galaxies. The distances are impossible, the energies are prohibitive, communication breaks down, space expands, relativity imposes absolute limits, and our own fragile bodies collapse under the conditions of deep space. But perhaps there is a small sliver of hope in all this despair. Perhaps if we could at least fully comprehend how vast the universe is, how insignificant we are on its scale, we could find some comfort. So, let's explore exactly that. the brutal reality of cosmic distances, and what they truly mean when you map them with ruthless precision. There is a reason why astronomers use terms like light year or parsec instead of kilometers. It is not scientific pretension or unnecessary jargon. It is because the numbers in kilometers become so absurdly large that they lose all meaning. When you say that Andromeda is 24 quintillion kilometers away, your brain simply cannot process it. That is a number without context, without scale, without emotional meaning. But when you truly understand what that distance means, when you map it against what we can actually do, the despair becomes palpable. Let's start with something we can comprehend. The Moon is approximately 384,400 kilometers from Earth. Humans have been there. 12 people have walked on its surface. The journey took approximately 3 days with the technology of the 60s. It is distant, but achievable. It is the only frontier in space that we have truly crossed with our own bodies. Mars, our next target, is on average about 225 million kilometers away, approximately 586 times farther than the Moon. With current technology, a manned trip would take between 6 and 9 months. It is challenging, but feasible. Engineers are seriously working on manned missions to Mars. We could do it in the next decade or two, if we truly commit. Now, let's take the next leap. Proxima Centauri, the star closest to our Sun, is 4.24 light-years away. That is approximately 40 trillion kilometers. To put it in perspective, if the distance to the Moon is 1 centimeter on a model scale, Proxima Centauri would be more than 3 kilometers away. With the technology of Voyager 1, our fastest spacecraft, it would take us approximately 73,000 years to arrive. 73,000 years. All of human civilization, from the first cities in Mesopotamia until today, is barely 1/3 of that time. The most optimistic proposals for advanced propulsion, like the Breakthrough Starshot project, which plans to use solar sails pushed by giant lasers, suggest that we could send microscopic probes to Proxima Centauri in approximately 20 years, traveling at 20% of the speed of light. Microscopic probes, not humans, not even car-sized robots, chips the size of your fingernail with tiny cameras. And that is the best we can conceive of, with known physics and an investment of billions of dollars. For a manned mission to Proxima Centauri, using realistic propulsion, we are talking about journeys of several centuries, multiple generations, living and dying in transit. And that is just to reach the nearest star. Just to cross approximately 0.0004% of the diameter of the Milky Way. The Milky Way is approximately 100,000 light-years in diameter. We are located approximately 26,000 light-years from the galactic center in one of the spiral arms. If we wanted to travel to the other side of our own galaxy, say 80,000 light-years away, with the technology of Breakthrough Starshot, it would take 400,000 years. 400,000 years. Neanderthals walked the Earth 400,000 years ago. Homo sapiens as a species has barely been in existence for 300,000 years. And remember, that is within our galaxy. That is our cosmic backyard. Now, let's jump to the intergalactic abyss. Andromeda, at 2.5 million light-years, is approximately 25 times more distant than the entire diameter of the Milky Way. If our entire galaxy is the size of a €1 coin, Andromeda is more than 2 meters away, and the space between them is not normal, empty space. It is a near-perfect vacuum, the emptiest space that exists in the universe. The density of matter in intergalactic space is approximately 1 atom per cubic meter. In some places, 1 atom per several cubic meters. It is a vacuum of a purity that we could never recreate in a laboratory. To reach Andromeda with Starshot technology would take 12.5 million years. From the time the first apes began to evolve in Africa until today, approximately 25 million years have passed. You would need half of that entire evolutionary time to make that journey. By the time you arrived, if anything arrived, humans would have evolved into something completely unrecognizable, or would have gone extinct long ago. But Andromeda is the exception. It is part of our local group, a cluster of approximately 54 galaxies, gravitationally bound to each other. The local group is approximately 10 million light-years in diameter. Within this group, there are perhaps half a dozen galaxies that we could theoretically target with ships. The Triangulum Galaxy, at 3 million light-years. The Magellanic Clouds, dwarf satellite galaxies of the Milky Way, at 163,000 and 200,000 light-years, respectively. These are our cosmic neighbors, our immediate galactic family, and yet they are so incomprehensibly far away that reaching them would require technologies bordering on theoretical physics and time periods that exceed the history of our species. Beyond the local group, the distances become truly cosmic in their scale. The nearest galaxy cluster is the Virgo cluster, at approximately 65 million light-years. It contains approximately 100 galaxies. With starshot technology, it would take you 325 million years to reach it. The dinosaurs dominated the Earth for approximately 165 million years. You would need almost double that entire period to make that journey. And Virgo is our local supercluster. Beyond it, there are other superclusters, each containing tens of thousands of galaxies, separated by cosmic voids, hundreds of millions of light-years across. The Coma supercluster, at 330 million light-years. The Great Attractor, a gravitational anomaly toward which our local group is moving, at approximately 250 million light-years. Shapley, the most massive supercluster in our nearby universe, at approximately 650 million light-years. These places are so distant that the light we see from them left when the dinosaurs still dominated the Earth, when the first mammals were mouse-sized creatures hiding in burrows. We are seeing the deep past of those places, and reaching them would require technologies and time periods that are simply incompatible with any meaningful concept of civilization or even of a biological species. And all of this is still within the nearby universe. The observable universe has a radius of approximately 46.5 billion light-years. That is due to the expansion of space. The light from objects now at that distance has taken 13.8 billion years to reach us, almost the entire age of the universe. But those objects have moved away due to the expansion while their light was traveling. But remember the Hubble horizon we discussed earlier. Beyond approximately 4.6 billion light-years, galaxies are moving away faster than even light can travel to reach them. Approximately 94% of the galaxies in the observable universe are beyond that horizon. They are observable in the sense that we can see their ancient light, but they are unreachable in any practical sense. Astronomers use something called the cosmic distance ladder to measure these vast expanses. It is a hierarchy of methods, each calibrated against the previous one, each extending our reach a little further. Stellar parallax for nearby stars, Cepheid variables for nearby galaxies, type Ia supernovae for cosmological distances. And every step on this ladder reveals that the universe is even more vast than the previous step suggested. There is something profoundly humbling in mapping the universe with precision. It is not just that we are small, although we are. It is that we are trapped in a minuscule region of an incomprehensibly vast cosmos, with no conceivable way to escape that region. It is like discovering you live on a tiny island in an infinite ocean, except this ocean is made of lethal vacuum and is actively expanding to ensure you can never swim to another island. There are approximately 2 trillion galaxies in the observable universe. 2 trillion, each containing hundreds of billions of stars, each star, potentially, with planets. The number of potential worlds is so vast that we literally cannot comprehend it. And of all those worlds, of all those possibilities, our species has meaningful access to exactly one, Earth. With extreme effort and advanced technology, We might perhaps colonize a few other bodies in our solar system. Mars, probably. Perhaps moons of Jupiter or Saturn. With enormous luck and multiple technological leaps, we might be able to send generation ships to a few nearby star systems, establishing small colonies that would likely die out or evolve into something non-human. And with technologies that border on the impossible, and resource commitments that exceed everything our civilization has ever done, maybe, just maybe, we could send expeditions to other galaxies in the local group. Expeditions that would take millions of years, that would completely break communication with home, that would be essentially irrelevant to the civilization that launched them. This is the map of our prison. A pale blue dot, suspended in a sunbeam, as Carl Sagan called it, surrounded by a solar system that we could marginally explore, contained within a galaxy that we could theoretically navigate over millions of years, and that galaxy, floating in a local group that marks the absolute limits of any conceivable expansion. Beyond those limits, the universe continues on scales that make our largest numbers seem trivial. But for us, for any biological civilization limited by the laws of physics, those expanses might as well be infinite. They are unreachable, not because we lack the technology, although we do, but because the fundamental laws of the universe guarantee that they remain forever out of reach. And yet, despite all this despair, despite all these insurmountable barriers, humanity continues to dream of the stars. It continues to imagine warp drives and wormholes and dimensional shortcuts that would allow us to cheat these limitations. It continues to cling to the hope that science fiction will eventually become scientific reality. So, let's examine those hopes, one by one, and see if any can survive the encounter with real physics. For decades, science fiction has sold us a vision of the future, where humanity escapes its planetary prison and expands across the cosmos. Star Trek showed us the warp drive. Star Wars gave us hyperspeed. Battlestar Galactica introduced us to instantaneous FTL jumps. Interstellar seduced us with traversable wormholes. These stories are beautiful, inspiring, full of hope, and all of them, absolutely all of them, depend on physics that is either completely impossible or so profoundly improbable that we might as well call it magic. It is not the writer's fault. Their job is to tell exciting stories, not to give physics lessons, but they have created generations of people who genuinely believe that intergalactic travel is just a matter of time and technological development. That eventually, we will discover the trick, the loophole in the laws of the universe, that will allow us to bypass the limitations. So, let's examine the most popular solutions from science fiction and see why each one falls apart when you confront it with real physics. Let's start with the most iconic, the warp drive from Star Trek. The idea is elegant. Instead of moving the ship through space, you contract space in front of you and expand space behind you. You create a bubble of space-time that carries you with it, as you surf a wave of distorted space. Technically, you are not traveling faster than light through space, so you do not violate relativity. Space itself moves, and you go with it. This idea is not completely fabricated. In 1994, the physicist Miguel Alcubierre published a paper showing that Einstein's equations of general relativity technically allow for this space-time geometry. The paper caused excitement because it seemed we finally had a mathematical solution for faster-than-light travel that did not openly violate known laws. But the enthusiasm was short-lived. When physicists examined the equations more closely, they discovered devastating problems. The first is energy. To create a warp bubble the size of a spacecraft, the Alcubierre equations require amounts of negative energy equivalent to the mass energy of the entire planet Jupiter. Negative energy? We are not talking about antimatter, which is normal matter with an opposite charge. We are talking about energy with negative density, something that has negative pressure and repulsive gravity. Does negative energy exist? Technically, there is a quantum phenomenon called the Casimir effect, which produces tiny amounts of something that behaves like negative energy. Two extremely close metal plates in a vacuum experience an attractive force due to quantum fluctuations. But the quantities are ridiculously small, on the order of piconewtons. And no one has any idea how to amplify this to macroscopic quantities, much less to the mass energy of Jupiter. But let's assume you can magically generate negative energy. The second problem is causality. Later analyses of the Alcubierre metric show that you inevitably create closed, time-like curves, loops in time that allow for violations of causality. You could arrive at your destination before you departed. You could,